In this video, we'll look at regression models where one or more variables is in log form. So I'm returning here to an example you've seen before, the relationship between education and earnings. So earnings is the outcome, education is the explanatory variable. You know this captures the linear association between these two variables. I went back to the NLSY 97 data and redid our scatter plot, but here, to focus more on the relationship between education and earnings, I'm looking at average earnings for every particular year of education. So instead of seeing all the different people with a high school diploma in this data set, you're seeing the average of those people. And same for a college degree over here, okay? And especially because, the distribution of earnings is so wide, sort of compressing it into the averages by each year of education here, it really lets us look for nonlinear relationships in a better way. This is an example of what's called a bin scatter plot, okay? And the marker sizes are proportional to the number of people in each group. And you can see that a line fits this, reasonably well, but the slope of the relationship is actually flatter for most of the distribution of X, and then there's this jump at higher levels of education. So we have some options here. We'll talk later about how you can use categorical variables to sort of describe this type of relationship. But if you wanted to fit a continuous relationship between y and x here, I would say it'd be very tempting to use a curve, something like this, to fit the relationship. All right, that's flatter here and then getting steeper, steeper, steeper as we get to higher values of x. And so what we can do in this case actually is, instead of using earnings on the left-hand side, we can use the log of earnings. So by log here, we mean the natural log, ln. Y here, I'll write it generically. And then we have x, thinking of it as education here. This is a linear regression because when we say linear regression, we mean the model's linear in the parameters, that's the betas, not necessarily linear in the variables. The disadvantage of a log transformation is it's hard to interpret variables in log form, but we can use the following property to get nice interpretations out of this. Okay? And the property is that if a variable is in log form, then changes in a variable, as long as they're small changes in the variable, okay, changes in log y are approximately equal to proportional changes in y. So everywhere we see something that's hard to interpret, like a change in log y, which is this object right here, delta log y, we can replace that with something that's easier to think about, a proportional change, or we might scale it to a percentage change in that variable. And that's what's on the right-hand side here, okay? Is delta y, that's an absolute change over a level of y. So that's a proportional change on the right-hand side. And these things are, again, approximately equal if the change involved is small. And again, the usefulness of this is it lets us turn something that's harder to think about because of that log transformation into something that might be quite natural to think about. Okay, and what this does is it enables a set of interpretations that look like the ones that you see on the table, which might look a little intimidating at first, but once you see some examples, I hope you'll get the hang of it pretty quickly. Okay, so this table, which you'll have on your formula sheet, you need to know how to use it, is showing you, all right, there's 4 different possible combinations of whether y is in log form and then whether x is in log form. Okay, and they're all here. You're familiar with the standard case. If someone has 2 more years of education, multiply that change 2 by the slope, and you get a certain increase in predicted earnings. Okay, that's the standard thing that you've seen. What we just saw is an example of this. Okay, and what we're going to say there is, all right, if this is log earnings on years of education, then a change in education. What we can do is we can take our slope estimate and scale it to from proportion to percent. Okay, that's what the 100 is doing, and say there's a certain approximate percentage change in the underlying y variable, which is earnings. Okay, notice that even though y is in log form over here, there's no log function over here. That's what that property we just looked at is doing. It's enabling us to go from thinking about the log of a variable to thinking about, okay, changes in that log y, changes in log earnings are approximately equal to proportional changes in earnings. All right, and this is, skipping down to the bottom here, This is something that people are used to thinking about. Okay, so like earnings gaps between demographic groups, or like someone's raise year over year, is often expressed in percentage terms. Okay, so for a variable that where it's natural to think about proportional changes or differences, or percentage changes or differences, right, such as earnings, it can be really natural to work with the log transformation. Okay, there's two other cases here that you'll kind of encounter through examples, right? One where we regress y on log x, and there we're thinking about proportional changes in x going with level changes in y, and then where y and x on the last line here are both in log form. Then we have proportional or percentage changes in y going with proportional or percentage changes in x right here. Percent change in y being related to percent change in x, right? Especially if you imagine dividing through by this percent change in x to the other side, that should look familiar to you. It's an elasticity, this beta 1 hat. Okay, so that comes up a lot in economics because again, beta 1 hat then has this nice elasticity interpretation. All right, so again, we'll work through the examples of these in class, but that gives you hopefully a basic idea of the fact that we can log transform certain types of variables, and that it leads to interpretations that involve proportional or percent changes in the variables that have been logged.